Hello everyone, welcome to Mind Maps. This is part 4 of electronic spectra of transition metal complex. We'll start with the electronic spectra of octahedral and tetrahedral complex. And we'll see the example of zinc plus and how the electronic spectra of trans and cis isomers differ in square plane. Okay, so let's start. As you can see, this is an electronic spectra, two complex, combined spectra of two complexes. The first one is CO, Cl4 2 minus, and the second one is COH2 2 plus. Right? So this is one. This is the second one. Okay? One, and the blue one is the second one. As you can see the color difference. Okay? The second one, the tetrahedral complex is intense. Okay? And the octahedral one is a bit pale. So what happens is in an octahedral complex, okay, I'm sorry for the drawing. Okay. So what happens in octahedral? The field is symmetrical. Okay. Field is symmetrical. So G to D transition takes place. D to D. Okay. Although it is forbidden, this transition is forbidden. Okay. This should not give any color at all. But what happens is the peak that we see there is the absorption is very low. It still happens. Why? Because of Bybronic coupling, intermixing of states, and spin orbital interaction. These were a few reasons that we discussed in the previous lecture. So as you can see, there is G to G transition that is forbidden. But in case of tetrahedral, okay, tetrahedral, what happens? In case of tetrahedral, the field is unsymmetrical. Okay, so G to G does not take place. Okay, so we can overcome the Laporte selection rule. That's why this is intense. Okay, this is intense. The tetrahedral complex is intense. Blue color. Why? Because the wavelength that is being absorbed falls in the blue region of visible spectrum, and the other one is pale. Even though this transition should not take place D to D or G to G, but still takes place due to various factors that we have already discussed. But tetrahedral field is unsymmetrical. Okay, so G to G transition does not take place. So this is like what allowed. Okay, so the next slide will Z2 plus. Okay, if we write the electronic configuration, argon, PD10, 4L0. Okay, so is levels from the orbital diagram, filling of orbitals. It looks like this. Okay, it's D10. If you calculate the CFSE delta O, that we get is 0. Okay, so when the CFSE is 0, no splitting takes place, there is no. Okay, so Z2 plus complexes are colorless. Okay, and that's clear. The next one is cis and trans. C. Now this is a metal. We'll use it out two isomers. This is trans. and this is cis. Okay, now I'll show you something. As you can see, the transition when we go from metal ion towards A1, okay, and when we move the same direction in the opposite, um, in the negative direction or whatever, along the same line towards A2, we encounter the same atom. So this has a center of symmetry. Alright, so what happens? The transition is G to G, which we already know is spin forbidden. Okay, it's not spin forbidden, it's electrolytic forbidden. The transition does not take place from G to G. Okay, so these are pale, maybe very less. But in case of cis, the same size, there is no I. That means there is no center of symmetry. This is unsymmetrical. So that's why these are more intense. These complexes are Na2, B2 type, in which cis is intense. I hope this was clear and you enjoyed this lecture. Please stay tuned for the coming video lectures in which we will be discussing the orbital diagrams in a shortcut, perhaps because we can cut a lot of details that are not to be remembered, only to be understood. Only those parts will be keeping. Thank you for watching.